In this video, I will show you the procedure to solve a partial differential equation. Before you can use this video, you need to be able to separate a PDE into a system of ordinary differential equations, find non-trivial solutions of a boundary value problem, and expand the function into a Fourier sine or cosine series. As an example, I will use a PDE that is different from the ones that you are going to solve at first. The idea is that you focus on the procedure and do not get distracted by the specific solutions. Variable u is the vertical displacement. It is a function of position x and time t. The PDE is second order in x, so it needs two boundary conditions. Here the solution is fixed to 0 at two endpoints 0 and L. The PDE is also second order in time, t, so it needs two initial conditions. Here the initial velocity equals 0 and the initial displacement is given by function f. Now that the problem has been defined, we can solve it. The solution procedure has 5 steps. The first step is to separate the variables. In our case, u of x and t is assumed to be the product of a function x of x and a function t of t. It is a good idea to separate the conditions first. There are 4 conditions. 3 of them are homogeneous. They state that u, or derivative of u, is equal to 0. Separate the homogeneous conditions. The first condition can be rewritten as x at 0 times t of t equals 0. When a product equals 0, one of the factors has to be 0. So either x at 0 or t of t is equal to 0. The second option is not a practical one, because then u would be 0 for all t, a trivial solution. So we conclude that only x at 0 should be 0. We can do the same for the boundary condition at the other end. So we conclude that x at L also equals 0. And the condition that the initial velocity equals 0 yields that the initial derivative of t is equal to 0. Note that the non-homogeneous condition cannot be separated in a useful way. We see that we have only one condition for function t and 2 for function x. This determines the order in which we are going to solve the separated equations. We start with x because we can clamp the solution for x on both sides and thus limit the number of non-trivial solutions as much as possible. In the third step, we will then solve for t. Now we can separate the partial differential equation. Separation can be done in several ways. Some are more convenient than others. Here you see a separation with the derivative function in the denominator. However, the separated equations are useless when sigma is equal to 0. This is not a good way to separate. You should keep the derivatives in the numerator. This is the best way to separate this PDE. Of course, you could use a different sign for sigma or use a different separation constant altogether. As we are going to solve the equation for x first, we want that equation to be as simple as possible. That's why we have put the gammas in the equation for t. Step 2. Solve the first equation. In this case, we start with x. Investigate all possible values of sigma, negative sigma, 0 and positive sigma, and find which values give non-trivial solutions x. These are the only sigma for which there are non-trivial solutions. X is then a sine function with an undetermined amplitude a1. Now the third step, solve the second equation. In our case, the equation for t. Of course, we are only using the values of sigma where there are non-trivial x. Calculating t for trivial x is a waste of time. This ordinary differential equation has cosines and sines as solutions. When we apply the homogeneous condition for t, the solution for t is a cosine. The amplitude of t is again undetermined. We have found non-trivial sine functions for x and cosines for t. For each n, the combination x times t is a solution. Because the PDE is linear, the sum of two of these solutions is also a solution, and the sum of 3 of them as well. There's a solution for every n, and the sum is again a solution. The general solution is an infinite series of functions. Note that each term has its own constant Cn. For each n, the amplitude of the term may be different. In step 5, the known coefficients Cn are determined with the last condition. The initial u is given by function f. So we substitute t equal to 0 in the general solution for u. And we see that f has to be expanded into a series of sine functions, all with a period of 2l. So the extension of the function has to be odd. The Fourier coefficients are a different constant value Cn for each n. And here's the solution. To summarize, in this course you should solve partial differential equations in the 5 steps. First, separate the variables. Then, solve the first ODE and find non-trivial solutions. In step 3, solve the other ODE. Then, combine the solutions into a series. In the last step, apply the last condition, and that usually involves a Fourier series. Go ahead and start solving your own partial differential equations.